Hello, for data communications and networking class today, Ajahn Uttana will talk about how to decode the circuit codes. Okay, we have talked about how to encode it before, and now we will talk about a simple way to decode the circuit code. Okay, basically decode means that you detect the error, and if you detect it, then you correct it. Okay, but in this class, since we have very short time, okay, I will teach you how to detect first, and maybe in the next slide I will explain a little bit about how to correct simple error. Okay, as I told you before, we have another class that we go into detail, which is applied coding. Actually, my research is in channel coding, so you can ask me in details, okay, of you want to know. Okay, so anyway, we have the data here, and then we get into the encoder. Then you will get the code word, right? Code word. And the data, maybe we call it vector U, code word we call it vector V, and then we may have a modulator, something like that, okay? But we will skip it in terms of the, we talked about coding. So we get into channel. Okay, channel. And the channel will cause like noises, interference. Okay, so the receive sequence will be can be different, okay, from the code word due to noises. Okay, so then we have decoder, and the decoder will make decision, okay, detect errors and correct them if they can, and we get the decoded data. Okay, so this is U with a hat. Receive sequence, we call it R. Okay, the U with the hat or the decoded data can be different from the data, okay, if you decode wrong. Okay, but if you decode correctly, then it will be the same. Okay, now to check for errors, okay, so the receiver want to check if there is any error. Okay, so the receiver, you divide the receive sequence R by the generator sequence G. Okay, so you test whether this remainder of R divided by G is 0 or not, or whether R is divisible by G or not. Okay, if the remainder is 0, then you assume that there is no error or no error is detected. So you will use this as like it is correct, okay, and you will send the data part to the user, okay, to the destination. But if the remainder is not 0, then you detect some errors, okay, and if you can may correct it, okay, or you may notify the other side, the sender, that there's something wrong. Okay, so this one is sure that there is some error in the receive sequence if the remainder is not 0. Now if the receive sequence contain no errors, okay, it will be the same as the code word V, right? No error, so it's the same as the code word. Okay, and since by design we decide that the remainder of V over G divided by G is 0, this one I skip the proof. Okay, as I said, you can ask me about this if you want. Okay, anyway, it's by design because when we have like any data, okay, we just tell you the concept a little bit. We have the data, and you put the parity check, okay, and you combine it and you get a code word, right? So how to get the parity check? You make the parity check so that the code word is divisible by G. Okay, so now you can separate between like any receive sequence that is not a code word and the code word, okay, the set of the code word. The property of these two sets that are different is that the code words are all divisible by G. If it's not divisible by G, if any sequence is not divisible by G, then it's not a code word. So this is how you separate the code word from the non-code word. Okay, so since R equal to G, okay, then if since r equal to v, if there is no error, then because we decide that v is divisible by g, then r in this case is divisible by g2. Okay, and the decoding methods, okay, for the cyclic code we have 3 methods as the encoding method. Okay, and this is how we checked, okay, whether it is divisible by g or not. Okay, let's look at examples. Okay, modulo 2 arithmetic first. Okay, if we have g, again, first bit on the left is usually most significant bit if I don't say anything. Okay, so we have g 4 bits. Okay, and r is 7 bits. So we compute so this is r, right, divisible by g or not, so we make long division. Okay, so you have 1 1 1 0 1 0 0, so you divided by 1 0 and 1, so you have 1 0 1 1 here, and then if it is the same, then it's 0, and this is different, so you get 1. This is different, you get 1. Okay, and this is going down, so you get 1. So you get 1 0 1 1, then you put you multiply the 1 0 1 of g by 1, so you get 1 0 and 1 here, and then this is chipped a little bit. Okay, so this is going down. Okay, so you get 0 here, 0 0 0. So this is all zeros, right? This is the remainder, and we may call it syndrome S. Okay, so you can define the remainder of r over g as a syndrome vector S. Okay, so the syndrome will tell you, okay, if you detect errors or not, and it can help you with error correction also. Okay, anyway, the remainder is 0, rx assume no error. Okay, now the first 4 bits are output as data. How do you know that which bit are data? Okay, first you have to know the nk of the code first. Okay, r has 7 bit, right, and r has n bit, so n equal to 7. Okay, now g has how many bit? G has n minus k plus 1 bit equal to 4. Okay, so 7 minus k plus 1 equal to 4, k equal to 4. Okay, so you have 4 bits here, code okay, and you know that this is no error, so it's the same as v, right? And v is equal to 2 to the b minus ku plus b, so b is what? 3 bits, right? A minus k equal to 3, so b equal to 3 bits, so this is b. So the first is the u, okay, that is shifted to the left. Okay, so 1 1 1 0 is u. Okay, so this is output as data, which is the same as the data in the encoding examples. Okay, so this is correct, and this is how you calculate it as I just explained on the top of the slide here. Okay, next we will decode by polynomials. Okay, this is a second method. Okay, you can choose either methods. Okay, the modulo 2 additions, arithmetic, or the polynomials. Okay, or the chip register also. They must give all the same result. Okay, now consider all the vector that we talked about before, and we have also the receive sequence vector. We put it in the polynomial form. Okay, using dummy variable x. The receive sequence have n bits. Okay, so we start with r sub n minus 1 to r0. Okay, rx is internal polynomial is r sub n minus 1 multiplied by x to the n minus 1 plus until r0. Okay, for example, you have r here again. This is most significant bit. Okay, this is the same values as the last example. You have x to the 6th, x to the 5th, x to the 4th, and x squared. Okay, so you get rx like this, and you test whether this is 0 or not. How to do that? You make long division. Okay, so this is your gx, this is your rx from before, and find whether there is any error in the rx. Okay, this is rx, this is gx. Okay, so you have x to the 6th, right? So but this is x cubed, so you have x cubed here. You multiply this, okay, by x multiply, okay, by x cubed, you get x to the 6 plus x to the 4th plus x cubed. And the same, if it is the same, it's cancel, okay? If you have only one of them, then you go down, okay, like this. And then you have x to the 5th, right? So, and you have x cubed here, so you have result is x squared. So x squared, okay, multiply by x squared, you have x to the 5th plus x cubed plus x squared. Then it becomes 0, no error, okay? Syndrome or SX equal to 0, so no errors, okay? So then you know that this is Vx, okay. And in this case, you have to know NK, which is have to be given to you, 7,4, because if it is not given to you, you don't know the length of n, right? Because Ix can have like any terms, okay? Ix can be anything, okay? It can be x to the x squared only, okay? Even though it have 7 bits, okay? Because the previous bit can be all zeros, okay? Anyway, so this is Vx, so you know that the first 4 term, okay, and the ux, okay, and this is the bx, okay. You can also convert to v, so 1 1 1 0 1 0 0, so this is u and this is b, okay. So this is the end of the slide.